All right, so we were working last class on graphs of rational functions, and it looked like it was pretty hard for all of you. So I want to make sure that we have some idea of what's going on and how you can identify the different features. So we got to start with our parent function, y equals 1 over x. And what I want you to notice when you get off the bat here is that there's two disconnected pieces. And the piece in the top right is saying that your y values are 1 divided by a positive number. And that means that you end up with positive y values as well. Over here, your y values are 1 divided by a negative number. So that means that you have negative values over there. So that's why you have one arm in the top right quadrant and another arm in the bottom left quadrant. The other thing I want you to notice is that this line right here is a boundary that your graph never crosses, as is this line right here. It's a boundary. And those are called asymptotes. So the line y equals 0 is a horizontal line, and it is called the horizontal asymptote. The reason you have a horizontal asymptote is because you are starting with the number 1 and you are dividing it. If you divide by bigger and bigger numbers, you get smaller and smaller answers. 1 divided by 10 is small. 1 divided by 100 is even smaller. 1 divided by a million is even smaller still. Your answers will never actually equal 0, but they will get as close as you could possibly want to 0. So as I zoom out along this line here, the values get closer and closer and closer to 0, never reaching it. And that's what the word asymptote means. You never get to the point. Asymptote means a, not, sim, same, and tote is like a location. So it's not reaching the same location. And so that's what the word from the Greek is saying, is that your function never reaches that exact location. Because you can never divide to reach exactly 0, but you can get as close as you want. And it's the same idea on the left side. It's just that you have 1 divided by negative 10. So it's negative 0.1. Divided by negative 100, negative 0.01. So the values just mirror on that side. Similarly, if you divide by small numbers, you get big answers. And so if you have 1 divided by a really small number, you get a big answer. And that's why you see the graph shooting up like this. If you think about it, 1 divided by a tenth is 10. 1 divided by a hundredth is 100. And you have the same idea here, that 1 divided by negative small is just negative big. And that's why it shoots down like that. So now that you have the basic 1 over x, what we start doing is looking at different versions of rational functions and seeing what their properties are. The first thing I'll do is move this to 1 over x minus 3. Before, I had a vertical asymptote at x equals 0. Now I have a vertical asymptote here. Vertical asymptote at x equals 3. Why is it at x equals 3? Because if I tried to make x equal 3, I would do 1 over 3 minus 3, and that's 1 divided by 0. Can't divide by 0. So that's why there's a gap right there. Notice that my horizontal asymptote is still in the same location. Because if I plug in a big number like 100 or 1,000 or a million, I'm still doing that same idea of 1 divided by a big number, very close to 0. If I do a negative big number, same idea, still very close to 0. I can do one other thing that I should show you here. If I put a negative number on top, they switch places. Because instead of it being now a positive divided by a positive over here and a positive divided by a negative, if I put a negative number on top of my fraction, it switches now. So that's why it's negative divided by positive in the bottom right and negative divided by negative in the top left. Okay, so just be aware of that. Now things can get even a little bit more complicated if we start putting factors on the numerator. So let's try that, x plus 2. Now what I want you to notice is we have four things that we can really identify about the graph. We have a vertical asymptote that's still in the same place for the same reason. X equals 3 because that makes the denominator 0. But we also have now an x-intercept. Before, we could never reach 0 because the top was 1. You could never do 1 divided by a number to equal 0. But if your top number is x plus 2, you can make x plus 2 equal 0. And that happens if x equals negative 2. And that means that if you plugged in negative 2 to your entire function, look what happens. Oops, negative 2. For both my x's, I get 0 over negative 5. That's a 0. That's why I have an x-intercept here at negative 2 comma 0. I have my vertical asymptote still at the same place, but my horizontal asymptote is now at y equals 1. Why is it at y equals 1? The reason is, before, when I was plugging in big numbers, I said 1 divided by a big number is little. Well, now I actually have a big number on top because x plus 2 would be like a million plus 2. And x minus 3 would be like a million minus 3. Those numbers are almost identical. A million plus 2 and a million minus 3 are almost identical numbers. If you divide two things that are almost identical, you'll get the number 1 as an answer. And the logic I'm using there is if the two numbers are exactly the same, then you get exactly 1. So if the two numbers are almost the same, you get almost, but not quite 1. And that's what asymptote means. Remember, you can get as close as you want to 1 without ever reaching it. If I change this function a little bit more, so let's make it instead 2x plus 2. Now, a couple things changed. My x-intercept changed to negative 1, and my horizontal asymptote changed to y equals 2. Why did it change to y equals 2? The reason is, if you look at the top and the bottom, and if I plug in big numbers like a million, now the top is like 2 million and the bottom is like almost 1 million. And so that comes out to be really close to 2. So in general, what you can do for the horizontal asymptote is you look at the ratio of leading terms. Notice that the vertical asymptote completely depends on the number on the bottom. If I make it x minus 5, now the vertical asymptote is at x equals 5. If I make it x plus 5, the vertical asymptote's at negative 5. So the vertical asymptote is just the zeros of the denominator. The x-intercept is the zeros of the numerator. And the y-intercept is always the same thing. The y-intercept is for every function ever. This is not a special rational function thing. If you plug in x equals 0, what do you get for y? So the y-intercept is always plug in x equals 0. And if you look right here, if I plug in x equals 0, I get 2/5, which agrees right here with 0.4. Okay, so I'm just going to show you one more example, but then I'm going to stop the video because I don't want it to get too long. Because I'm just trying to focus on the four basic pieces: horizontal asymptote, vertical asymptote, x-intercept, and y-intercept. So here is the last little bit of complication that we can throw in there. The top and the bottom don't have to be linear. You could have a top of x squared minus 1 and have a bottom of x squared minus 3x minus 4. Let me change that. Let me make x squared minus 5. Let me do this. 5x minus 14. So you can have it like this in 3 different pieces. If I change it to 6, it looks only like 2 pieces. But really, if you follow these same 4 notes that I have there on the side, you'll get most of it. In another video, I will explain why this being a 6 only has one vertical asymptote, only has 2 arms to it. But if I change it to a 14, it has 3 different pieces right there. But that's a little bit more than I want to go into right now. But I just want to show you that these can get a little more complicated, but keep in mind the basic pieces that you can do the ratio of the leading terms, you can do the zeros of the denominator, you can do the zeros of the numerator, and you can plug in x equals 0 and you'll get a lot of the information you need. So thanks for watching. Please ask questions.